With the publication of the theory of relativity, Einstein attributed 4 dimensions to the universe, 3 spatial and 1 temporal. However, a few years later, physicists Theodore Kaluza and Oscar Klein proposed a theory suggesting that the universe had 5 dimensions. The addition of the 5th dimension was necessary to unify gravity, as described by Einstein, with light. This theory led several physicists to consider the idea that the universe could have many more dimensions, up to 10, a number considered essential to formulate a theory capable of describing every phenomenon in the universe. The thought that the universe could have more dimensions than we perceive is a concept difficult to imagine, primarily because our experience suggests that the reality we live in consists of 3 spatial dimensions. We can move in 3 directions, forward and backward, right and left, up and down. But why should we think that other dimensions exist? However, our experience doesn't always allow us to describe reality objectively, and we could make mistakes. For example, we are convinced that time flows the same for everyone, regardless of where we are or whether we are moving or still. If an hour has passed for us, it should be the same for anyone else. However, Einstein, with the theory of relativity, showed that time is not fixed, but is influenced by speed and gravity. Time flows more slowly if we move at speeds close to that of light or if we are near strong gravitational fields, such as black holes. For instance, the clock of an astronaut traveling on the International Space Station runs slower than one on Earth due to the ISS's speed. Moreover, very sensitive instruments have detected that a clock at sea level runs more slowly than one in the mountains, because the closer we are to the center of the Earth, the stronger the gravitational force that slows down time. Although these differences are imperceptible, they demonstrate how our idea of time based on daily experience is wrong. Einstein's relativity also changed our conception of space, showing how the presence of matter warps space and time. This helps us understand that our perception of reality is not enough to describe it accurately. Although our experience suggests that we live in 3 spatial dimensions, this does not mean that it is truly the case. In 1919, mathematician and physicist Theodore Kaluza revolutionized physics by hypothesizing that the universe was not composed of 4 dimensions, the 3 spatial ones plus time, but 5. Kaluza used this 5th dimension to unify 2 of the most important theories of the time, Einstein's gravity and Maxwell's electromagnetism. Einstein had shown that gravity is not a force that propagates through space, but a manifestation of the curvature of space itself, generated by bodies with mass. Based on this concept, Kaluza proposed that electromagnetism was also an effect of the curvature of the 5th dimension. However, Kaluza couldn't explain why we do not see the 5th dimension. Oscar Klein answered this in 1926, suggesting that the universe contains both extended and curled-up dimensions, invisible to the naked eye. To understand better, imagine a rope stretched between 2 points. From afar, we only see its length and extended dimension. But an ant on that rope could move around its circumference, a curled-up and invisible dimension. Klein proposed that the universe has 3 extended spatial dimensions and a 4th, very small and curled up. This theory became known as the Kaluza-Klein theory. According to Klein, this extra 5th dimension exists throughout the universe, but it is so small that it cannot be perceived. Over the years, physicists discovered new subatomic particles and developed the Standard Model, which described 3 of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, and electromagnetism. Gravity was missing, and physicists found themselves at a dead end in attempting to unify the forces into a single theory. In the 1980s, string theory began gaining traction. This theory suggests that matter is made up of tiny strings, whose vibrations determine the properties of particles. However, string theory only works if we consider 9 spatial dimensions. Adding time, we reach a total of 10 dimensions, just as Kaluza and Klein had suggested. The 6 extra dimensions of string theory would be extremely small, similar to those of Kaluza-Klein, and curled up on themselves. These hidden dimensions would influence the properties of the particles we observe in our 3-dimensional universe. However, we currently do not have the tools to detect these extra dimensions. If we were able to prove their existence in the future, we could finally confirm the validity of string theory and get closer to formulating a unified theory of the universe. Although relativity is the most accurate theory for describing gravity, and the Standard Model has managed to unify 3 of the 4 fundamental forces, string theory remains a promising but still unproven path to understanding the universe on a deeper level. Thank you for watching. If you enjoyed the video, please leave a like and subscribe to the channel.